Hello, my fad-setting physics students. So in this one, we're going to talk about some of the basics as to angular motion, or as it could be better said, spinning things. Okay, so when things are spinning, there's definitely motion, but it's going in this circular path, and so there's a few things that are a little bit different. And so one of the things that is different is basically how you express this motion. Now you could say that if I had a point right here and it went all the way around this circle in 1 second, I would get 1 revolution per second, right? So you could talk about angular motion in the sense of revolutions per second, and you might see that like on a tachometer in a car where it tells you how many times you have a revolution of your engine per minute. So oftentimes we have tachometers in our cars that do that. And but in chemistry, we don't use revolutions per second in our calculations. Instead, we use a thing called a radian. Now, what is a radian? Well, a radian is simply an angle right here in which the arc subtends the radius. And so this idea, as soon as you get an angle that's great enough so that this arc right here is able to subtend this radius, or in another way you could say sort of equal or cancel out this radius, it's a radian. And so in a complete circle, you actually have, for 1 revolution, you'll actually have 2 pi radians. Okay? So anytime you have revolutions per second, you could multiply that by 2 pi, and you'll convert it then to radians per second. And so why is it important to understand the idea of radians per second? Well, radians per second is how we measure angular velocity. So we've talked about velocity in the linear sense, which is how much distance you're covering per second. So angular velocity is how many radians you cover per second. So angular velocity is radians per second. And so we can also have then anything that speeds up angular motion then is going to be an angular acceleration. So you can have it go faster or slower. So what's an acceleration going to be? Well, an angular acceleration is going to just be a radian per second squared. Or you could also express that as a change in the angular velocity over a change in time. So you can calculate angular acceleration if you know angular velocity change. So say something is starting from 0 and going up, to 3. Say you have something going from 0 to 3 in, let's say, 2 seconds, right? So I have an angular acceleration of 1.5, right? So it's pretty simple to solve for angular acceleration. Now, one of the other things, too, that we need to think about is that if you accelerate something in an angular motion like this, if you were to stop pulling it toward the center, if you were to take away the centripetal force, that thing would then be converted directly to a linear velocity or a linear acceleration. So linear acceleration, as we've talked about before, is here as well. The only difference between linear acceleration and angular acceleration is this radius that you're traveling around this circle. So it's pretty simple. If you ever want to convert any of these things to linear, say if you wanted to say, okay, if I know my angular acceleration, what is my linear acceleration? Well, you just multiply it times the radius, and that's going to be your linear acceleration. Same thing with the angular velocity. If you were to multiply that times the radius, well, that's going to give you your linear velocity. Or let's just say we had distance. Our distance, where we're talking about, for acceleration, we have a change in distance over a change in time, right? Just we have a change in radians over change in time. So distance, you would simply say, okay, well, what the distance in meters is actually going to equal my radius times my number of radians, right? My radians. So this is a pretty simple way to take anything that's linear and actually convert it to circular, and also we can accelerate something in a circular fashion really fast, and then let it go, and zip, it's got an acceleration that would have taken you a whole lot of linear space to do, but you could do it in a circular way and then release it and sling, boom. And that's the idea of a slingshot that you spin over your head, kind of the David and Goliath kind of idea. And so with that sort of a slingshot, you can get a rock or something going the speed of a bullet, essentially. So this is kind of just a little snapshot of what is angular motion, what is a radian, how do you convert from radians. So there's 2 pi radians in a revolution, or you could also do it the other way around. You could say a radian equals 1/2 pi revolution. So you could convert it both ways, backwards and forwards. So that shouldn't be too much of a problem for you. And also one thing in angular motion is that the motion, if it's counterclockwise like this, is seen as positive. So this motion right here that I'm currently showing is counterclockwise, is positive. And so whenever we're looking at the direction, because these are all vector quantities, if I'm counterclockwise, that equals positive. If I'm clockwise, then of course that equals the negative direction. So in angular motion, counterclockwise spin is considered positive, whereas the clockwise is considered negative. Don't ask me why. I'm not quite sure as to the reason for that. And so I think that that sort of wraps up that idea, and we're going to use some of these concepts then as we go on and we talk about some of the ways that angular motion is used and how we calculate forces, and we use the conversion of a linear maybe velocity to an angular one. So if the wheel, or if the car is moving at this linear speed, well then the wheel will have this angular speed. So if the car is accelerating, then the wheel will have this angular acceleration, but you can convert back and forth, and you can easily see how one goes to the other. And then the idea of radians versus revolutions, oftentimes you're going to get given revolutions per second, so you got to convert back and forth between radians and that in order to solve these problems. So hopefully that helps just kind of give you an initial understanding of the idea of angular motion, and we'll continue on with some more rotational dynamics questions and problems that get a little bit more difficult and incorporate a few more aspects.